All right, one more thing. One more thing real quick, and then we'll get done for today. Um, Another type of energy. So potential energy was the energy based on position or orientation with respect to other objects. Kinetic energy is the energy of motion. So if an object is moving, then it has with it kinetic energy. Kinetic energy is 1/2 mass times velocity squared. And it's important to note that it is velocity squared. So if I were to double the velocity of the object, keep the mass the same, what would I be doing to the energy of the object? Quadrupling it. I'd be squaring that double. Well, energy is conserved. So if I take an object from a certain height and I say that it has some amount of potential energy and I drop it, I can figure out how fast it should be going when it gets to the ground. These equations are actually come before the kinematics equations. Kinematics is derived energy. So we'll show you that later on. So we're going to go ahead and define this as K sub T for translational kinetic energy. Later on, we're going to define K sub R, which is rotational kinetic energy. If this ball were sliding along the table, it would be translating. It's moving in the X, Y, or Z directions. If this ball were spinning, then it would be rotating. And that spinning ball would also have some energy. We'll get into that when we get into rotation. Bowling has both. It's rolling, spinning around, and it's translating. Now I can give this energy just like I can give potential energy. So if I have an object that's just sitting there and I give it a little push, then I'm applying a force on that object over some amount of distance, and then I would give it kinetic energy. So it's just another type of energy that work can create. So if I have a ball of mass m and I apply a force on that ball, and I apply that force over some amount of distance, call it x, then the work is equal to that force times the distance x. And the ball is going to speed up, and therefore it's going to gain a certain amount of kinetic energy. So that can also be equal to 1/2 mv squared in this case. In this case. So work doesn't have to just be giving something potential energy. It can also give something kinetic energy, or it can give something spring potential energy. Work is just giving it energy or taking it away. It doesn't say any specific type of energy. It could be all three. If I were to go to a soccer ball and give it a kick, if that ball went up, then it gained potential. If it's moving, then it gained kinetic. If the ball compressed, then it gained elastic. So the work that I do or the force that I apply can give it any type of energy. In this situation, the work I'm doing is giving it kinetic energy. In the previous situation, the work that I did gave it potential energy. I can give it any type of energy. And again, this has to be an external force. If a ball were rolling along the table, or a box was sliding along a table, and that box stopped, was work done on that object? If I take a textbook and I give it some initial velocity, and then later on, that box stops, like things do. Was work done on that object?
Yeah, it depends. Yes.
How will you know for sure?
Yeah, the table part of the system or not?
Is the table part of the system or not? That's a good question. Does it matter whether the table is a part of the system?
Yes.
How would you include it as a part of the system?
Oh, if it is part of the system, friction has. Well, what stops if no force acts against the velocity? Nothing.
Let's come back to that question. That's an interesting idea. We are not, and we often don't, take tables as a part of our system. So we'll look at a situation where we do. Including the table makes it very, very complicated. That's why I don't want to do it quite yet. Yeah. We'll get into that later. If this thing stops, so a table is not a part of our system. So is work done? You were the component saying yes, yes, yes. How do I know if work was done? The energy changed. Not just the kinetic energy stopped, because I can throw something up in the air and the kinetic energy stops, but work was still done on the system. Maybe. We'll get into that one too. If the energy changes, if total energy changes, sorry to make it passive, but that's just how it came out. If the total amount of energy of a system changes, then work must have been done in order to change that. My emails.
Hey, Robbie, cyclic dies.
What type or types of energy did this thing have when it started? It had kinetic energy. What type or types of energy did it have when it finished? It had zero energy. So it had some energy, we'll call it K.
Well, are you assuming it's on the surface?
Yeah. It doesn't make any difference, though, in this case, because we're not talking about potential energy. It had some kinetic energy, and then later on it didn't. So work must have been done. If work was done, there must be a force that does the work. What force does the work? Friction. How much work did friction do in this case?
The amount.
Not K. Negative K.
Oh, good job.
Oh.
Show it off.
The change in energy is equal to the final amount of energy minus the initial amount of energy. So the change in energy in this case is 0 minus K. The thing had some positive work, and then it had some positive energy, then it didn't have any energy. So there must have been negative work. So the change in energy is equal to minus K. Change in energy is work. So work is equal to minus K. So if the work was negative, how does the force relate to the displacement? They're in opposite directions. Which way was the force on that box? This way. Which way did the box displace?
To the left. On the left.
When the displacement and the force vector are in opposite directions, the work was negative, which we can show that it is. Are there other forces acting on this box other than friction?
No.
Well, MG and N.
Normal force and mg.
Those don't affect.
Are those doing work on our system?
No.
Why not?
It doesn't move that way.
They're perpendicular to the displacement vector. Good. So if I added up all of the work done on this object, I would say work done by normal force, nothing. Work done by gravity, nothing. Work done by friction, negative. So it started with K. Work done by normal force doesn't change it. Work done by mg doesn't change it. Work done by friction loses K. And then it ends up with zero energy at the end. Good? Good.